on the 8th of August in the afternoon, but it's very low on the horizon. The moon phases, first quarter the 12th of August, last quarter the 26th of August, full moon is the 19th of August, new moon the 4th, and then we're actually going to do a presentation at the Redham School, I think, in 4 ways on the 2nd, which is Friday. The planets, Mercury is visible in the evenings, Venus in the evening as well, Mars early morning, Jupiter early morning, Saturn is from the whole evening from about 9 o'clock, Uranus early morning, and Neptune is visible from midnight. The Eta Iradanus meteor showers is visible from the end of July till the middle of August after midnight, and I think around about in the middle of that day it's the most active. And that's it. Thanks.
Great. Okay. I must say I had a look at Uranus this morning, as well as Neptune last night.
Nice.
They're both blue. And very small and round.
Yeah. Okay, should I carry on?
Yes, please, Wayne.
Cool. Okay, let me check. Okay, there we go. And then we'll go here. Okay, guys. So just going to take you through basically how do we go from seeing complete blackness into these images that you see online and all of these amazing images that like the Hubble shares and James Webb shares, and obviously the equipment I'm going to be using is nothing like that, but the principles remain the same. Plus, also, when you look through a telescope, it looks nothing like the images you see online. I just want to kind of describe a bit why it looks nothing like it. So our eyes are pretty terrible in comparison to cameras for dim objects. They've definitely got advantages, but your eye roughly will take an exposure, an image every 10 seconds, and then your brain does all of the integration and the merging of images from there. But it is not a very long exposure. It's a fairly short exposure. Our eyes are also not incredibly good at dim, faint objects. They're adapted to more the daytime, and that's where they're better suited at. So there are ways of improving night vision, dark adaptation, averted vision to see objects, but that is not going to get you the full color and the full faint details that are out there. So I'm going to take you through kind of why as well, because it's I think people don't realize how incredibly faint the signal is from these objects. The images may look good, but we do a lot of processing on these images. As I said, like the exposure time, I've got an example object here. I think my total exposure time is just over 37 hours on it. Your eyes are going to be nowhere near that. So you're not going to expect to match some sort of getting all the very, very faint photons in and get all of the detail that you can see. Sensitivity, I don't have an exact figure on like your quantum efficiency of your eyes, but it's in a few percent, whereas the newer cameras are in the 90+% bracket of efficiency. That is how efficient it is at turning all the photons that arrive into the sensor sites and converting them into a signal. So obviously you're fighting a losing battle here. And then light pollution. So there are ways we have as astrophotographers to kind of avoid some light pollution. There are also ways to avoid light pollution as a visual observer and like if you look up. But we'll get into that. And these are the main things that we are fighting. And also our Hubble and like James Webb has such an advantage. They don't have the atmosphere. They don't have light pollution. They get around. They have many, many, many hours of exposure time. And their cameras and equipment there is significantly more advanced than what we've got. So exposure times, and I've covered that briefly. Your eyes take a snapshot of roughly 10 times a second. And I do a minimum of 3 hours of exposure for any picture. that's a quick snapshot for an astrophoto. That's a very quick image. Normally, I won't bother doing anything less than about 12 hours of exposure time. That's just because the stuff is very faint. When you're looking to get the real interesting detail out of it, you need the time to gather all of that very, very faint data. And it makes processing a bit easier because the data is a bit cleaner. And sensitivity, your eyes can see typically around 5th magnitude stars. I go down on the images to about 18th, 19th magnitude. And just for reference, that the magnitude is a logarithmic scale, so it is hugely more sensitive than your eyes. And again, as I said, the quantum efficiency is not even comparable in terms of a camera and your eyes. Okay, light pollution. If you've ever been out to a rural area, a dark site, a very, in the middle of nowhere, probably around a Bortle 2 to 3. 1 is quite rare unless you're in like the middle of the Karoo or absolutely nowhere. But you will immediately see finding things in the sky becomes really, really difficult because there's suddenly stars and Milky Way and everything else that you can't see if you step outside and look up. See, tonight's not a great night because it's quite cloudy tonight, but the difference is significant. This here is an example for anyone who doesn't quite know like the difference. This is Orion. This is a site that I found that gives you a demo on the Bortle scale as to kind of the difference. Bortle 1 being your best stars, Bortle 9 being your worst. This is Orion. You will see the classic belts and arms and legs, but you do not see the nebula, the Orion Nebula. The whole set sits over here. Bernard's loop sits around here. You can just see it. I don't know how well this is coming across in the video and the sharing, but you can just kind of see it here. So you can see these things, but you're also not going to see colors as easily as this. Your eyes tend to not be in dim light, not be very color sensitive. So you do lose a bit of the color. It is possible to see some of it, but you need very dark skies to be able to see this because you need that blackness of space. So these are the big things that you're going to be fighting. Now, there are ways to work around it for imaging. And whatever tricks I can talk about, whatever things that we do, nothing beats a dark sky. So some of the guys currently are in the middle of the Karoo at the moment. They're on a imaging trip. It's 9-hour drive or something from here. It's in the middle of nowhere. There is nothing around. That's a Bortle 1 sky. That is pitch black. It is fantastic for imaging because you can get your broadband, so your full color imaging is great because you don't have the light pollution getting in the way. You don't have everything else that influences the image that like from the back garden that we have. Narrowband is still better in dark skies. You get better contrast. It's not as different as broadband. It's like the difference is smaller, and I'll kind of cover why. But yeah, it's if you can get away to a dark place, go there. It is so much a much better experience. No matter what we do here, we're never going to get close to that. And the other thing we can do, a monochromatic camera, so your black and white camera with narrowband filters saves a lot of our ability to image from the back garden. So unfortunately, very, very few of us will have the luxury of a remote imaging site that can live in a dark location, and you can image as often as you have clear skies. I know a couple of people around the world, they have this, and there are also telescopes you can rent time on and image in these dark areas. But barring all of that and the quite significant costs of hosting in these remote locations, you have to find other ways around it. Color cameras, obviously, they do work. Don't get me wrong, there's nothing wrong with them, but they are not as efficient as a monochromatic camera when you're using narrowband filters, because you've already got you're essentially imaging through 2 filters for a color camera. So you are losing out on efficiency, you are losing out, but it is possible to do. You can get great results with it. You're just not as efficient. Now, the straight out of a camera, this is a 300-second image. This is straight out of the camera, and it is not stretched at all. Here is a star that is sitting over here. Now, this is a 300-second image through hydrogen alpha. So it is a narrowband filter, and they're just looking at just the hydrogen in the sky. And why is it so black? Because this is the histogram of that image. Here is all the data sitting on this very edge over here. So everything in this image is basically black. And don't misunderstand, every image that will come from anything in space is going to look like this initially. All of your data is going to sit on this side just because the image, the data that comes from it, the amount of photons we get is very, very small. And this is a comparison of a DSLR image. This is was taken with a normal DSLR camera during the day. And I just put this into the same tool to show kind of the relative brightness and where your histogram sits. Obviously, in a camera, they do stretch it a bit slightly. So this is like a one-to-one comparison directly loaded in. Nothing done to the image in PixInsight. For those who don't know, that's what a lot of people use to edit astrophotography images. I will switch to it just now to show you, when we get to the end, a couple of things that our steps I'll run through. But you can immediately see the amount of data that's sitting outside of pure blackness, and you can actually see a usable image. Now, also this here is a 1/322nd exposure. So it is 96,000 times faster than the image before. 300 seconds versus a 0.003125 second image. If I did 1 second exposure here, this would basically be completely white. We wouldn't be able to see a thing. It would be flat out, no image, no data left in the image because it is too bright. So it may look dark, but the time difference is significant in these two. Now, that image that I showed you before, this is it stretched. So stretching is just taking that histogram, pulling the data out across, and you can see here is this lump, and this is where the center of this data is sitting. And now you can suddenly see everything inside the image. Now, this may look like a lot here, but in this unstretched state, the difference of these bright areas, well, bright being relative, these bright areas here in the darker skies is about 4% of the, 100% being completely white, 0% being completely black. That's about a 4% difference. This is about sitting at about 0.5% of, and that's my light pollution, that's the background noise, the background sort of level. And then this is about 4%. So it's about 3.5% above complete nothing. This middle of the star here, absolute middle there, is about, in this image, is sitting at about 40% or so of the image. So even this thing, which looks very, very bright, is still, there's a significant amount of nothing, that a headroom in this image. And this is what we start getting. I mean, anyone who's done any imaging, you'll recognize these kind of images as they come in, and we will set up the telescope, set it up imaging, and take as many images as we can throughout the night. The reason we're going to do all of that, before I get onto that, this is the stretched daytime image. So this is, you can see now, this will look like a normal image. It's taken that, and this is the before, this is the after of that histogram. You can see how it's stretched it in a similar way. It aims for this sort of median here as the center of the peak when it does the auto stretch. And you can see how this looks a perfectly usable image, but huge amount more data. You can see it's a much, much brighter compared to this previous one here. The max is very low compared to this here, which is peaking out over here. So hopefully that goes some way to explaining the differences of amount of data that comes in into the cameras. It is not a lot. It is very, very faint. If you don't stretch it, you don't see a thing. And also remember, this is a 300-second image, so it's a lot of exposure time, and these are very sensitive cameras, cool down to very low temperatures to try and remove as much additional noise data as possible, and so on. So yeah, it's a significant difference to what you can expect from a daytime and a nighttime image. So why do we do lots of exposure? So you don't really ever want to do a single, well, it's not possible to do a single 37-hour exposure because you're going to run out of dark. So that's one. We also have imperfect gear. A lot of us are not running extremely high-end mounts. So tracking for a very, very long period of time, things happen. It's not the mechanical things, nature of it is not perfect, so you can get some movement. You might get a bit of wind at night, knocking the telescope, blurring it a bit. So if you try to image for an 8-hour image, for example, you would have some blurring, you would have some errors in it. You're also going to hit the meridian at the telescope. So the telescope has to flip sides of the mount. It can only go sort of up to complete vertical, then it needs to flip and go down the other side. Otherwise, the telescope hits the mount. So at some point in the night, it flips sides. Now, this could be any point in the night. It depends on where the image is in the sky, because it's a meridian in the sky. It's not like midnight where it'll flip. It could be 8 o'clock. It could be 2 o'clock in the morning. It just depends on where it sits in the sky. So all of that leads you to having a limited amount of time that you can image at once. And then what you also have is there's read noise. So every time you take an image, some electronic noise is added via the circuitry that reads that out from the camera. That is a kind of a fixed level based on your temperatures and the gain that you have. So all of that is something that is added to every single image. Now, what you can do is you can get rid of that noise, and I'll cover that. And the other thing is the cameras have a limited depth or amount of data it can collect. So every photon that arrives, the quantum efficiency determines how many of those get converted into an electron in the well of each photosite. So that sits at about 90%, sometimes a bit lower, 60%. So only 90% of those photons arrive. And depending on the well size, which could be 50,000 electrons, 20,000 electrons, 100,000, that needs to be converted from that to a digital signal. And there's some imperfect conversion that happens there. I'll cover that a bit later, but that also determines on like what you can see and how we can try and use the stacking of multiple images to get around some of this. Stacking also improves your signal to noise ratio. So because between every couple of images, what we do is something called dithering, which slightly moves the telescope. So it moves it by a couple of pixels, and you're deliberately doing this every few images. So what that does is because it bumps it slightly, any patterned noise, any fixed sort of artifacts in the image, such as your banding that happens or fixed noise that you can get, gets averaged out when you start stacking all of the images together. We are also fighting light pollution and all of this. So as you're also imaging all of that. So you want to try and get a little of that as possible. And as it moves through the sky, you get different parts of the sky will have different areas of light pollution. The moon is a big source of light pollution. The guys will know who image how bright that moon can be and how bright it can wash out your images, even if you're not close to it, especially if you're in broadband and taking up images that are somewhat close to the moon in a couple of degrees. You may as well not bother in a way, because it can be too bright. It can actually wash out all the detail. So whilst it sounds strange, moon is light pollution. Earth's atmosphere reflecting the zodiacal light that comes in, all of this gets in the way of us imaging. Now you can't get rid of all of these. Some of the light pollution moves to the dark side. You can't really get rid of it. You can reduce it via narrowband imaging, but you still have a level of light pollution in there. So that is part of what we have to fight with. Okay, read noise. It is low. Okay, it's a couple of electrons. It's really not huge. but it adds up. And the more you don't do anything about it and you have these really, really long images, you can see it noise. So if you can, I'll show you now in PixInsight when I jump to it, you can definitely see how much more noisy these images are. And that noise is completely random. So we want to get rid of it. And that is just the more you stack these images, what it does stacking in very short terms is it puts the images on top of each other. Like if you would in Photoshop, layer images, aligned to the star, so it finds all the stars, aligns the images so they all slightly shifted from each other because of the dithering, finds them, stacks them on top of each other, and you will, because the noise is random, and having enough of it cancels it out, cancels it to a point where it's not a thing anymore. And what that lets you do is it brings out the detail that you didn't see. So if you remember that original image of a single one there, I'll show you the fully stacked one just now, where that goes from 5 minutes to 14 hours of imaging time. You'll see how much more detail comes out, and that's a big difference of why we do this. So a signal to noise ratio. So signal to noise ratio is the measure of obviously the signal to the noise in the image, and it's typically measured in decibels. The single image that I showed is a signal to noise ratio of about 15 decibels. The final stacked one is about 30 decibels. It's not twice. The decibels are a logarithmic scale. So it's about 32 times better quality, signal to noise ratio quality of a stacked image than a single image. All of this means you can process images further. You get more detail out of it. You're not fighting that random noise, which makes it difficult to see details. And then you can kind of get more out of it. You can pull more. The better quality, the smoother the image, you can stretch it more. You can do before it starts breaking down and you getting like a banding in your images and so on. The imperfect conversion. So the other thing with cameras is you have a range, depending on the camera you have and the hardware you're using. You've got an analog to digital unit, which converts it from your analog signal in your wells, which is the bucket of electrons, into a digital signal. So you go from 12-bit, 14-bit, 16-bit is your typical cameras. Your 12-bit has 4,096 gray levels, and a 16-bit camera, well, it's a 16-bit converter, will have 65,536 gray levels. This doesn't automatically mean better. It's a bit of a complicated relationship of the well size and the bit depth. So what it does is it takes that well size and essentially divides it into buckets, each bucket being a certain number. So if you have 100,000, let's say 40,000 in the 12-bit camera, you will have buckets of 10 each, roughly. And in the 16-bit and a 40,000 and a 60,000 well depth, you will have a buckets of less than one each. You can't really go less than one, but one each. So that would let you convert like a much, much smoother. One electron arriving means one additional gray level. For the 12-bit camera, you have to get 10 of these electrons arriving to mean an extra color. So depending on the camera and depending on how the size is and all of that, how it matches out, you can essentially lose data or not have if you don't image long enough. And so it's a balance of imaging time, of not being too short, imaging too long where you get blurring because of your equipment, and also trying to get enough of those gray levels to bump over into the next number. If you go too far in it and you fill it well up, you start losing data because more electrons in it actually can spill over into other wells. So you can start kind of getting that blur, and you'll see stars look bloated, they get big. You don't want that to happen. You want to try and avoid that. And you can also hit the full well. You always want to have some headroom. If you hit the top of it, if you hit the well and there's no more to grow into, you're essentially losing data because you've hit that top bit and there's no more to add to it. So imaging more is not going to get you more. You're just losing data of those other ones. So it's a complicated relationship of all of this that you have to try and manage. when you start imaging, you will figure it out about what your imaging time should be for your equipment. Some equipment, like especially your faster telescopes and a very sensitive camera, is going to hit those limits faster. Something like the one that I've imaged, this one is an f8, so it's relatively slow telescope. It takes quite a while to get data in. Something like Tion's Rasa is an f2 or 2.1. Very, very, very fast telescope. So that fills up where I do 5 minutes, he does 30 seconds. You know, it's a difference, and it's a equipment difference. You just, depending on what you want. I've got a much longer focal length, so I get closer up to objects than he would. So it's this big difference that you constantly have to deal with in imaging. And it's a game we play of trying to figure out what's the best setup. The other thing that we have a problem with is atmospheric dispersion. That convolutes an image, so basically it blurs out your details. There are ways to recover it. It helps. It definitely sharpens up images and can undo the blurring of the atmosphere. Not perfect. It's a mathematical formula doing it, so it's not like magic that's happening. It's just trying to undo the spread that happens. Okay, other things that we have that get in the way of imaging is optical train errors. So this is in your telescope system, you have you could have internal reflections. So if you have a particularly shiny surface in something, you can actually get some artifacts from that. You could have a gap somewhere or a light leak somewhere. Now we're talking about very, very small things. I mean, like a hair width gap somewhere in something could result in a light leak, and you will see that as an artifact in your image. And the other one, because our cameras are connected to an open telescope, and essentially the lens is open for the most part. So depending on your like something like a refractor will have essentially it's a lens, so you don't have that open to the camera open to the atmosphere. But unlike a Newtonian or anything like that, your camera sensor has got a glass filter in front of it. Otherwise, it is exposed to all of the atmospheric conditions. So you'll see here, these are dust. This is dust that is collected on the sensor window. So what we do is we take these flats. They do a few things. This vignetting that we have around the areas here, this darkening of the corners, that's just the light on from the telescope is not fully illuminating the sensor 100% evenly. This is very minor on this. I know it looks bad, but this is a stretch, very drastically shown these differences. But it is there, and it helps correct that errors. And this dust, it removes these dust errors from the image, because you will never be able to keep that camera sensor perfectly clean. It's gonna always get dirty. Docks. So obviously, okay, so newer cameras, older cameras, they're gonna have different amounts of thermal noise. Every camera is gonna have some thermal noise. Some are significantly better. Thermal noise comes from the sensor incorrectly interpreting heat as photons. This is just a byproduct of the design and how they work. You will get these, like you can see, like this pixelation that happens and these brighter spots. These are the hot pixels. So this is the hot pixels and the general background thermal noise you have in the camera. Newer cameras tend not to have these glows on the edges here. This is called an amp glow. That comes from the electronic circuitry that sits around the camera that gets hot, and it causes this glow in the camera. This is a 300-second dark stack. So this is averaging all of that image over, this is multiple. I think this is 50 images of 300 seconds each, done in pure blackness, so camera covered, to highlight this. And what you do is you subtract this from the images that you take. To clean this up, it gets rid of this dark noise, and you have a nice clean image again. Even the cameras that don't have this amp glow, it's still advisable to use darks. Even if you have a low noise camera, still do it, because it's a trivial step. I've had these docks for over a year. You don't update them every night. You just keep reusing them. But what it does, it gets rid of that thermal background noise that you have. And even in the normal cameras, you'll see if you take a picture or a video in dark, you'll see it's very grainy. That's the thermal noise. So we want to try and get rid of as much of that as possible. The other way we do try and reduce that on the astronomical imaging cameras is by cooling the sensor. Normally in a normal camera, your sensor is just at ambient temperature, slightly hotter. So you'll probably see it sitting around 30 in a normal, say 20 degrees Celsius day. It could sit around 30, 36 degrees Celsius on that actual camera itself. That will be a massive amount of noise. These sensors are cooled with a little metal finger that actually touches the back of the sensor. That drops down into, so all of that is then locked in a sealed, hermetically sealed container. So no atmosphere can get into it, nothing can get into it. And that is a very dry, very, very dry atmosphere. Because what we do, that metal finger drops down and is cooled by some Peltier coolers, trying to drop that temperature as low as possible. I normally image at about minus 15 degrees Celsius on the sensor temperature. So not outside temperature, not temperature, like the actual sensor itself temperature sits at about minus 15. The lower you drop it, the lower the thermal noise goes. It is a battle because the cameras can only cool like 40 degrees or 35 degrees Celsius below ambient. So in winter, it's very easy to cool because our outside is sitting at 4 or 5 degrees Celsius, sometimes lower. Very easy to cool down to minus 15. In summer, when it's sitting at 20 degrees outside, it's quite hard. You're making that camera work quite hard to cool it down. So then I might up it up to about minus 10 just to make it possible for the camera cooler to keep up with cooling the sensor. The lower you go, the better it is, the less thermal noise you have. Typically, minus 10, minus 15 is where it starts plateauing at a low level. Like increasing the cooling further doesn't significantly improve things in these imaging ones. I know some of the other sensors and more advanced sensors can enjoy better results with even further cooling, but for the cameras we use, typically doesn't matter. So even if you try to take a normal camera and cool it on the outside, what you're not doing is not cooling the sensor itself. So you still have that problem. And if you cool it down without too cold, without being inside a sealed environment, you risk getting dew on the sensor, and water on any electronic device is never a good thing. So you've got to be careful if you're going to try and do it manually. It is possible to do some things, but it's not the same as a dedicated camera that's designed for this. And then light pollution. So light pollution depends on your Bortle rating of the sky, where you live. Like here in the middle of the city, we unfortunately have quite a high level of light pollution. There's nothing you can do about it unless you go to a dark sky. So there's no clever trickery here. It is kind of a fixed background noise. And why there's nothing you can really do about it, because if your signal coming from your object is lower than your light pollution level, you're not going to see it. You're not going to be able to, no matter how long you image for, no matter what you do, if that signal is not greater than that background level, you're not going to be able to do anything. So the only way you can get is to try and remove that, drop that background level, moving out to darker skies or remote imaging, or find that magical filter that cancels out light pollution, or hope for a really, really massive ESCOM blackout where we can get nice dark skies. So this is a fully stacked image of the one I showed previously. You will see there's a lot more faint detail sitting in the background here. There's a lot more structure visible here. This is 173,000 seconds. 173 300-second images for a total of nearly 52,000 seconds of imaging time, which is 14.4 hours of imaging. This is just for the one filter. So there's other filters I do. You will need about between 2 and 3 filters to get a color image. 16.6 million times more exposure time than that single DSLR image. Now, whilst this looks bright, it is still incredibly faint. The The dark parts here are sitting at about 0.9% brightness. The brightest areas sitting here are still sitting at about 6% of the total 100%. So think of it, 6 photons versus 0.9 photons out of a total of 100. Very, very, very faint detail. Even though you can see this detail in here, the actual difference in brightness levels is incredibly low. Even these stars, this brightest star over here, I checked the center of it, it's sitting about 52% brightness. So still very, very, very low light levels. Even in the brightest parts here, still dark. So yeah, like that's a lot of why it is so, to me, amazing that we can actually produce these images from with equipment we have sitting in our back garden. How incredibly faint these objects are. These images we make, kind of show it and it looks amazing. And then you go in to look at it through a telescope and you're not going to see anything like this. It is so, 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 so faint. And this is, nearly 15 hours of exposure time with dedicated equipment, a large telescope, and you still barely have any data there. To me, it's crazy that you can actually even get this image from our back gardens and with the equipment available to us. And then I just want to cover broadband versus narrowband. So I've got 2 images here of M20, red and hydrogen alpha. So this is your red one unstretched, hydrogen alpha unstretched. The red, you will see a lot more stars, and when I stretch it out, you will see, whilst this looks a lot, this is still about 50%. This is about 50% brighter in the backgrounds than this. When you properly stretch this out and pull out the data, you will find a lot more structure in your hydrogen alpha, and that's because of the area I'm in. It's bright. The light pollution is covering the details in the broadband. The narrowband, this hydrogen alpha narrowband is about a 5 nanometer filter that I've got. My oxygen and sulfur are 3 nanometers. And just for reference, light is 300 nanometers sort of width, with your red, green, and blues being about 100 each. So this is a fraction, allowing a fraction of the light in, about 5% of the light in case of HA, as to what a red filter would allow. And this is a 120-second stack versus a 5-minute stack. And this is about a couple of hours of each. But this is 120-second images versus a 5-minute. You can see here what I mean by the blooming. This star here is the same one here, but you can see its light has spilled out and covering a lot more of the image. Because it's so much brighter, this is starting to clip at 100%. Trying to avoid it with it, what I'll typically do, reduce stars, try and manage the stars in these images, and then bring in the detail from these. But you still get some info here, so you don't want to like completely throw away your RGB images. But that's the challenge you have with broadband. It's allowing a lot more light in. You get more data in, but you also get more of the background in, which you can't get rid of. So in our back gardens, broadband is very difficult. You need a lot of hours to get some interesting data out, and a lot of the time we can't see, like, galaxies not fun to image here, because all of that lovely detail is hidden. No matter how much time you do, you get muddy looking images. You don't get as great a detail. Look, we can still do some nice stuff, but you just don't get anywhere near what kind of quality you could do by going to the dark side. Okay, now I've spoken about all these monochrome images and these gray images. This is just how monochrome works. You've got the different filters. So the same object, this is, for those who don't know, this is the Helix Nebula. This is hydrogen, oxygen, and sulfur. Roughly the same amount of hours in each. You can see the massive structure differences. This hydrogen has this very like ring structure, almost nothing in the middle. Oxygen very strong in the middle, and it has these fantastic like streaks that are going out. I'll open it up in full thing and show, like, it's amazing like how like streaky it is. Sulfur, always sulfur. Sulfur is never has anything like your hydrogen and oxygen in terms of amount of data. That's just because it's a more rare element. You don't have as much of it. Hydrogen is the most abundant element. Sulfur is much further down. You don't have nearly as much of it available. It still adds detail. It still adds some structure. So that's why we image it. It's definitely worth like doing. But you can see like this is, I think this is 12 hours. It looks very faint. It is very faint. This has got very little info here, but it's still something to add. So what we do to go from here to one of these type of images is you assign, okay, we'll say this is green, this is blue, and this is red. Or we'll say that this is green, that this is red, and that this is green, and this is blue. You can do it in many, many ways. Here are some examples. This is hydrogen as red, sulfur 2 is green, and oxygen is blue. This is hydrogen is green, oxygen is blue, sulfur is red. And this is a special kind of merge called a 4-ax palette. It does a good job of trying to balance it out, especially if you've got some of these faint colors. It gets you quite pleasing looking images. There is no right and wrong way to do this here with narrowband, especially with broadband of red, green, and blue. Red goes to red, blue goes to blue, green goes to green. Okay, so that's pretty obvious and that's pretty easy. And why I say there's no wrong or right way to do this, hydrogen is red. If you want to look at the hydrogen HA emission line is red. It's more like your salmon pinky color. Sulfur 2 is also red, but that sits more in the blood red, the darker red spectrum. And oxygen is a teal color. So oxygen is similar to this color over here. It's just like tealy green. It's like almost sitting in between the blue and the green, slightly more on the blue side than the green. So if you've got two reds, trying to mix them together, you're going to get a red image and you're going to lose all of this other detail in here. You can't assign two colors to one channel. Well, you can merge them together, but then you've lost that structure difference that these two give you. So the Hubble palette, which is what you would see from the Hubble images, it's just been named that because of some of the images that you get. Sulfur goes to red, hydrogen goes to green, oxygen goes to blue, which is this one here. Obviously, this is not a very visually appealing image. It's very green. This is nowhere near what it actually looks like. This is closer to what it actually would look like in reality, because it's got your more reds and blues. Your eyes wouldn't see a massive difference between this. This would be like a darker red, like a more pinky red. But this is closer to what it is, and you'll see a lot of the images go into the blues, the green, the blues, the reds, and it goes some of those golden colors. Those golden colors come from the color balancing with sulfur and hydrogen, trying to get rid of some of this green. And then before I switch to, I'll switch to a demo now, but this is after imaging, after doing the stacking, after running it through. Takes quite a while to stack this. I think this stack took me about 45 minutes to running on this machine to put all these images together. After that, you do remove noise, undo the convolution. These are done via AI tools nowadays. You can still do it the original way, but it's significantly more manual, a lot harder to make mistakes. Well, yeah, a lot easier to make mistakes, a lot harder to get it right. And the AI tools do an extremely good job of it, sometimes, if not a lot better than we can do by ourselves, because they've been trained specifically on astronomical data to try and undo the effects of the atmosphere. So they're very, very good at it. Then what we do is stretch the data, so pull out these faint details, split out, depending on what now it depends on what you're imaging. If you're imaging something like these nebula, you want to remove the stars and the nebula, so you can focus on editing the nebula, because you don't want to oversaturate stars. You don't want to sharpen stars, otherwise you get very bad looking stars that look very like harsh, round, blotted circles versus a star. And an oversaturated star goes like straight to white. You lose some of the nuance of color in the stars. So what you want to do is split out these two, so you have the without the stars and with the stars, and you can do a lot heavier editing on the nebula, try and enhance the colors, try and enhance that structure that's there, and bring out the detail. And then there's some light sharpening that happens, and if you split these two out, you add the stars back in. Any questions before I move on to showing some of this?
Wayne, I'm just curious.
Yes.
Can you take photos from multiple sites, like in the Karoo and somewhere in Joburg, and then combine them, stack them?
Yes. So this image that I've got here, this Helix Nebula, this is actually done over 2 years. So this is over the space of 2 years. I did it so separate imaging times over these years. You can image it. You can put in images of different focal lengths. It obviously gets more complicated to do that because you've now got a wider field of view and a shorter field of view. It is much easier to have the same focal length. But if you have the same focal length from different locations, yes, you can. When you stack it, the software will rotate the images and try and get them to match. The best would be to take a reference image, share it, and use that to plate solve and to adjust your rotation of all your instruments so you have it all aligned properly. Then in your stacking, it doesn't have to throw away as much data on the edges, because if it has to rotate images, obviously you're going to have to cut out that error. So yes, you can. There's nothing stopping you from doing it. As I said, this is over 2 years. A lot of these images I'm doing now, I go back and add data on, and it's the same kind of thing. It's imaging from different locations. Your image doesn't change where you are in the world. It's too far away to actually have any like significant difference. I think your parallax shift is going to be so small in these images that your atmospheric dispersion is probably going to outweigh any sort of parallax shift that you have from shifting even one side of the Earth to the other. Cool. Let me shift to.
Sorry, Wayne, and another question, if I may, quickly. Thank you so much. This is fascinating. I'm really enjoying this. And I really appreciate the effort. But I notice here that you have the stretching before splitting the nebula and stars. I mean, I don't know why, but I've always done it the other way around. I guess I've always narrowband. I've always stretched the stars separately from the nebula. Do you have any strong views on that, or does it really matter?
How I do it is it's a multi kind of step process. I stretch a bit, and as the first stretch, the set of stretches, I do it in stages. The first set of stretches I do is to get the stars to a nice level. Then I split it out, and depending on what the nebula looks like, and if it's a fainter one, I'll stretch it more. If it's a very bright nebula, I might leave it as it is. I tend to do that first, so I get an idea of what the total thing looks like before I split. Because sometimes it's quite difficult to judge how bright those stars should be if you don't have it referenced on the thing. And you can always stretch again later on. So I tend to do like a light stretch in the beginning, split it out. But in practical terms of what you're doing, it doesn't matter. So you can do it first. You can do it in this linear state before stretching. You can do it post. Just don't overstretch the stars. Once you've overstretched, you've clipped data and you've lost it. So you just want to do those first stretches lightly. Don't stretch a very star-filled image of a nebula and forget about the stars looking at the nebula. If you do that, yes, you're going to have a problem. If you don't overdo stars, it's fine because you haven't clipped data yet and you haven't lost. Okay. PixInsight. Okay, so this is a fantastically user-friendly tool, and everyone who's ever tried to use this will know that this is an absolute nightmare to try and learn. It's complicated, but it is, when you've spent the time and when you've gone through it, it's incredibly powerful. So I've just I've saved this as a project. What I typically do is I keep all of these. These are the processes that I use. I've saved these off and keep them here. So if I open up one of these tools like this, local histogram equalization, I've got some starting values. I don't use the basic values that come off of these tools. I've just gone throughout working through this kind of found what works and saved. I do modify these. Every image is different. You almost never just drag and drop these on and process an image. There's too many differences in images. So I've got all of these here. And then what you do is you've got your light frames. Let me just, this is already got some noise reduction that applied to it. You can see it's not badly noisy. Let's have a quick look at this one here. Sorry, I just want to drag some things onto here quickly. Okay. So we just apply a quick screen stretch, and you'll see like this has got nothing applied to it. Okay, I haven't applied anything to these images yet. I was just double checking what I had done. So we've got these AI tools, blur exterminator, remove noise. These are amazingly easy compared to what we used to have to do for deconvolution. Deconvolution used to involve selecting the stars, so then the right kind of stars in the image as your sort of reference stars. It's for the algorithm to determine how much deconvolution to apply. So what it does is it looks at the PSF, the point spread function of the star, and tries and knows what the ideal should be of a star. Looks at that and it tries to undo that mathematically through some very complicated math, undoes that blurring. So deconvolution. Convolution is essentially blurring, applying a function to a thing to spread it out. Deconvolution reverses that and essentially sharpens it. So these tools obviously are not free, paid for tools, but it's if you have tried to do this yourself and you do this where you just simply, for the most part, I've largely keep the values the same. I don't need to change them all the time. I find something that works. Again, I do change it per image, but this makes a big difference in sort of just the speed of editing and the ease of it. So I'll just apply this quickly. I am running this in for those guys who don't run it. If you have a card that's capable, run it with CUDA extensions. It makes a huge difference in terms of time, going from minutes to seconds. And then let's see. Hopefully this comes through. Let me zoom in and show you the difference. Okay, so that's no deconvolution applied, and that's with deconvolution applied. Now, I don't know how well it's coming through, but you'll see like it sharpens up and brings out details. So this tries to undo that error that's come in through the atmosphere. If you look at the star here, you can see it sharpens up. It essentially tries to reduce that point spread of the star and make it more. And it has a byproduct. It looks at the stars because that's the only way you have like an actual reference of what it should look like. It doesn't understand a nebula, but because it applies this across the image, you can sharpen up and bring out details in the image. Then after that, we would apply denoise, which will go and try and remove all of this noise. And again, this is an AI-related tool. You can do this manually. It's a lot harder. Well, it's not hard. It's just more complicated. This is really easy. It's the normal manual way is a more trial and error because it's you're using various filters and so on to try and get the layers and get the detail, find out where the details in the image sit. This knows what to do. So if I can go in here, noise, no noise. As simple as dragging and dropping, and this gets you a pretty good image, an amazing amount of detail in here. And this you can apply to all of these, and I don't know again how well this is going to come through, but this is I was talking about. This oxygen has got this amazing amount of detail sitting in it. These very streaky lines coming out of it, which is so interesting to see, like what kind of detail you have. You'll see these are some dark globules in front of this, so you get some darkness over here. You'll see there's a slight patterning. It's easier to see when further out. A slight darkening around here. There's obviously less oxygen here than there is in the center here. Slightly less. This is the star that is the star that all this gas came from. Slightly darker here, more around here. So it's very interesting to see these structures. There's some slight structure up here, and good old sulfur. Yeah, shame, poor sulfur. It's always not nearly as much. In the brighter nebulae, you do get some really nice sulfur, but a lot of the dimmer objects and that there isn't a lot of sulfur. But it still adds. There is still something here. There's still this ring of stuff that is here. So it adds a little bit to the image. Now, you can either do this like a channel combination to go red, green, blue, and combine the colors, or you can do something like a 4x palette, which combines out to this kind of image here. Now, obviously, this background is way too high because this is a stretched image, way too high over here. You want to go and start stretching the image. Let's do that quickly. I typically use this generalized hyperbolic stretch because it gives quite a nice ability to control the stretch. And let's zoom in a bit. So we can start by this. And you see you pulling out this histogram here. Let me track it. Sorry, let me track these straight. You can see you pulling out the image here. This is your histogram. And as I go in, you can see it gets darker, gets way too much over there. I've crushed all of the images over there. So you've lost all of this detail. So this is part of the art in doing it. You don't want to do something like this. You don't want to go and smash it out because you lose all of the interesting data. You want to do it in stages. So as I was saying stuff like earlier, I will look at where my stars are going. If I hover over here, I don't know if you can see it, but at the bottom here, it'll give a readout of, say, this is sitting at 1. No, sorry, this is sitting at 0.1, and that is going to 0.7. That's sitting at fully out, maxed out now. So I don't want to do that. Obviously, that's too far in the stars. So you want to bring it in and not flash, not like mash your stars out. Otherwise, you still won. You want to not bring out all your stars. So this is showing me the bottom of the screen. I'm talking about this area over here. It's showing me the RGB readout, where you want to try and get it such that the stars are not done. Let's just assume that, without fiddling too much, that this is what you can do here is adjust how bright the dark is versus the light. So this allows, this is why I use this tool, because it lets me control colors and where it's stretching better. Let's just run that stretch quickly. Okay, so now this image is nonlinear. I no longer have this screen stretch applied. What we want to do is remove the stars. Again, another AR tool, because it makes removing stars very, very easy. Just a drag and drop, and it will go look for the stars, pull the stars out, and give me 2 images. One, and I've asked it for a star image. I can completely remove the stars if I want and not put them back, but I personally like adding stars back. So this will run quickly, remove the stars, and give me 2 images. So here's my star image, and here's my other nebula image. So what I was saying now, I'll go and run this general hyperbolic stretch again. Let's just select. You can also do a select on the image here. So if I want to stretch this section out here, or do I want to stretch the dark? Let me try and pull out these dark areas over here. So I'll select that and start trying to pull them out. So this is where we can go. We can see how far. Okay, see now at some point you're getting too much of the background. This is where you play, you fiddle. I'm not going to spend too much time, otherwise we'll spend hours doing this because it does take time. And now we leave the stars alone for a long, long time, because you don't want to, these operations that you're going to do now, you don't want to apply in the same level to the stars. Otherwise, you're going to kill your star colors and star quality. Curves. This is Photoshop curves. For anyone who's done any image editing, this is your normal curves that you have. Saturation, you can see your colors become a lot more saturated or desaturated. So depending on what you want is all the fiddling that you do. What I want to do now is my background is too bright. You can see there's the background. So what I want to do is pull that down. I want to try and see if I can pull this up. So this is sitting over here. So I can maybe pull that up a bit and then pull this up a bit. Okay. And reset that. And now let's say we want to apply some more saturation. Let's see where are the colors I want to increase saturation. If I drag it there, I see it's actually sitting in this area over here. So let me pull that up and pull that down. So what this is here, this is a high saturation, low saturation. Okay, Okay, these values are way too high for what a normal edit would be, but fine, an example. And you can see very saturated colors sit high up here. I might want to pull this down even more. So you can see this goes from a very like overly red and strange looking, you can get it to where you like it. Save that. And if you wanted to say, okay, I actually want more red in this because I prefer that color, I could up the red channel, leave it down. I can pull the red down in other areas, and maybe let's bring up some blue over here. Cool. Yeah, and you can keep fiddling with the image and doing what you want with it. This is where it's an interpretation of how you want to show this image and how you want to convert the colors. You want to bring out some more of these structural details here. Okay, we'll apply this local histogram equalization, which you can then, okay, I'll never ever do this right, but I bump it up to see where does the structure sit, at what point is the structure that I want to enhance sitting. So I say, no, that's not what I want. Maybe I can up the contrast limits. Okay, see, maybe you want to bring that out. Okay, let's go 0.5. 0.5. Okay, I'll apply that. And you keep working through an image, doing this to try and pull out where you want structure, where you want to show things. At the end, apply some sharpening. I've got these saved. This applies sharpening. I've got 2 of them, depending on what I want to sharpen. Let's just pluck this one on. What it'll do is it'll just add some sharpening around these details. So if you look here, unsharpened, sharpened, it just highlights it a bit more. You want to do this lightly. So these, I would never do it this quickly. This is just something, this is a lot of time spent fiddling, tweaking, adjusting slightly, because it's easy to overdo it. You want to do it subtly and slowly work your way towards the details you want. And then after all of that, what you want to do is add the stars back in. So I've got this is a pixel math process. Pixel math is great. Basically, it lets you do math on individual pixels. There's a huge amount you can do here in the tool. What this is doing is it's adding this image called RGB stars back into this operation of a screen operation. So Photoshop or any of the image editing programs, it's the screen transfer. Because when I remove the stars, I did the rescreen. That gives slightly better quality stars, especially over bright things, than just a straight removal. So it just blends it a bit better. So you need to combine it back. Bring the stars back and you're done. That sounds very, very simple. But yeah, this is hours of editing. You can see that this one I've spent more time on. I've pulled out some of this background detail a bit more. I'm still working on this. Going to be removing some of this, which I don't quite like this color here. It's got a bit of a background. I want to try and enhance these colors over here and the structure, but I need to bring down some of this background. And it's a lot of tweaking back and forth. This might be a bit oversaturated. You can see this going up to like 60% red here. I might want to bring that saturation down. It's a matter of playing with the image until you feel comfortable with it. But what you can see here is I've got a lot more of the structure that the oxygen was hinting at in the image, where you can see these striations coming out from the central point here, where it's obviously the stellar winds are blowing out. You can see some of the oxygen streaks that were in here. It's quite faint, but it's sitting there. And this is where, like, yeah, I spent time. This is probably about 8 hours of editing this image so far. And I will keep on going until I'm happy. Because yeah, it's a slow process. There is no right and wrong once you get to this. There are advisable guidelines, as in don't over sharpen, don't oversaturate. Like this is too much saturation, but don't oversaturate, don't over sharpen, because it starts looking fake. You want it to kind of look a bit natural. You want to kind of, the images are never perfect. If it looks too perfect, it looks fake. So like you'll see like an over sharpened image of a person also just looks wrong. It looks very wrong. But like a too blurry image of a person, like not in focus, also looks wrong. So you want to get the feeling it's in focus and it's sharp, but not over sharpened. So it's this balance you got to play. It's tweaking the value slightly, doing it slowly, adding it on slowly. And again, you've got a massive whole history here. So if I go show, where's my history? Should be here somewhere. You can see a full history of this image, of all the editing done on it. I can't see here. Okay, can't find it now. It used to sit down here. I must have moved it somewhere. Where you've got all the history of it, so I can go back, I can redo operations, I can see everything. So it's time consuming. Anyone who's done the editing of your normal imagery for like any photos you're doing, even a DSLR, this is a time consuming process to get it just right. But that goes from very almost nothing %. So if you look at the original images here, this is sitting at, you can see K equals 0.097. One here is 100% saturated. So this is very 9%. There's 10%, and this is a stretched 7%. Black over here 5. So very, very low values here, but that comes into this kind of image after a lot of fiddling. And now you've got your RGB values, no longer K. K is your black. RGB values, you can see the differences in here. So this is where you go through, you inspect your image. Am I oversaturating anything? I don't want to be oversaturating. I want to keep it, or shouldn't be oversaturated. Sorry, it's extremely tight. It's close to being oversaturated. Oh, this is just hitting 1 in the middle. So I'm okay with that. I'm okay with hitting 1 just in the middle of your stars, because it's kind of like your point light being okay. But I don't want to oversaturate these around here. Otherwise, you get this strange, very circular, hard-looking object, which looks unnatural. But yeah, that's the process of turning nothing into an image like this. And hopefully, it's given some appreciation of what's involved and why you can't see what you would be able to from like your eyes and your telescope. You're looking through the telescope to getting to this kind of final image. Any questions, Gus? No? Cool. Thank you, everyone. I mean, I think if there's no further questions or nothing anyone wants to ask, have a good evening and enjoy the rest of your evening. Again, feel free to message me or ask. I'll happily answer questions. Yes, Christoph.
No, I just wanted to say thank you. This was fascinating. I really appreciated the effort and I really enjoyed it. Thank you so much.
Oh, it's a pleasure. Thanks, guys.
Thanks from me as well, Wayne.
Cool. Have a good one. Yes, thank you. I will share I'll once the recording's finished processing, I will share and put it up somewhere.